Hi, this is an overview of our paper titled Multimodality as Supervision, Self-Supervised Specialization to the Test Environment via Multimodality. We study a few basic questions in this paper. First, we ask, can multimodality be leveraged as a source of self-supervision? Next, can multimodality substitute data? More specifically, can one use significantly less data when leveraging a rich set of modalities? And lastly, can a specialized model outperform state-of-the-art generalist models trained on large-scale internet-based datasets? We find that the answer to all these questions is a yes, which raises interesting points. It enables a scenario where the need for external internet-scale datasets for training foundation models is reduced, yet the model can achieve SOTA performance in a given application by leveraging multimodality without any access to external data. Many practical applications involve a user who is interested in deploying a vision model in their house. This could be a vision model for a household robot, an augmented reality device, or a domestic digital assistant. One key property in all these applications is they would operate exclusively within the user's house, or as we call it, the test space. The de facto approach for these applications is to use an off-the-shelf generalist model, pre-trained on large-scale external datasets like the internet. In this work, we show that we do not need large-scale external datasets like the internet to build performant models for such applications. We show that we can build state-of-the-art models for the test space by collecting unlabeled pre-training data in it. Additionally, collecting data in the test space and not relying on external sources also enables us to collect modality-rich data via any user device like a household robot. This is in contrast with external datasets like the internet, where such modality-rich data collection is infeasible due to the additional cost and unavailability of such sensory data acquisition over billions of images from disconnected external spaces. To this end, we develop multimodal test space training. It enables pre-training specialist models to a given test space by collecting unlabeled, multimodal data and perform self-supervised pre-training on it. This is in contrast with generalist models that rely on large-scale internet-based datasets. To perform self-supervised pre-training in the test space, we draw inspiration from findings in developmental psychology that suggest predicting the response of one sensor from another is a potent signal for learning representations of the physical world. Therefore, we leverage multimodality, or more specifically, cross-modal learning, as a signal for self-supervised learning for test space training. We implement this cross-modal learning by leveraging multimodal masked modeling as our objective. We provide more details on it later in the video. We show through extensive analysis and experiments that with multimodal test space training, we can leverage rich multimodal data from the test space to build a specialist model, which is more performant than internet-based generalists when deployed in the test space. The idea of our framework is to specialize a vision model in given test space by pre-training on it. It has 4 stages, namely data collection in the test space, self-supervised pre-training on this data, transferring the pre-trained model on a small labeled dataset from an external space, evaluating the model in the test space. The first stage of our framework is data collection in the test space. We collect data from various vantage points in the test space. In practice, this can be done using a walkthrough video or a robot exploring a space and recording random images. This data can be multimodal and contain 2 kinds of modalities. First, sensor-based modalities, namely RGB images, depth maps, surface normals, and canny edges. Moreover, we can create optional additional modalities using off-the-shelf networks to further expand our dataset. Using these modalities is akin to distilling and adapting powerful pre-trained networks in the test space for further improving the performance. In practice, this set of modalities can be significantly expanded to several common sensors, such as audio, motion, and occasionally haptic sensing present on household devices. We provide more details on it shortly. Next, we use cross-modal learning, or more specifically, predict the response of one sensor from another to perform self-supervised pre-training on this data. Once done pre-training, we use a small dataset with task-specific annotations to transfer the pre-trained model to a given task. Note that this dataset comes from an external space, as we do not want to assume we have access to task-specific labels in the test space. In the last stage, we evaluate the transferred model in the test space itself on 3 tasks: object detection, semantic segmentation, and image captioning. We present results on 3 datasets. Firstly, ScanNet++, which is a large-scale dataset with real-world indoor spaces, containing sub-millimeter resolution scans with registered DSLR images and commodity RGB stream from iPhone. Additionally, we also present results on Replica, which contains 3D scans of real-world spaces, and Procthor, which contains procedurally generated houses. These environments provide a controllable experimentation and ablation setup, while ScanNet++ is a real-world setup with real data from DSLR and iPhone cameras. As stated before, we use self-supervised learning on the data collected from the test space. We use multimodal masked modeling as our objective, since we found it to be the most performant. We present an analysis comparing various self-supervised objectives later on in the video. We start with sensor-based modalities. And we optionally further scale up our set of modalities by using off-the-shelf networks for pseudo-labeling. Specifically, neural network feature maps like clip and image bind, and output of task specialists for segmentation and detection are used as additional modalities. Now, using these set of sensory and additional pseudo-labeled modalities, we pre-train our model using masked modeling over these modalities. We call the resulting model TSTMM, Test Space Training Multimodal. We present results on semantic segmentation of test space training against various generalist baselines in ScanNet++. We use a video clip spanning a test space and do a frame-by-frame prediction for each method. As can be seen, the predictions from test space training are more accurate and more stable and consistent across viewpoints. We observe similar trends in the replica dataset as well. Predictions from TST are more consistent and stable across viewpoints. We also compare our model to Mask2Former, a semantic segmentation specialist network, and find that the predictions from the test space training model are higher quality and more stable. This suggests that despite being self-supervised, multimodal test space training is better alternative for semantic segmentation than using a task specialist model trained on large-scale supervised semantic segmentation data. Similar to semantic segmentation, we find TST is more stable and performant than relevant baselines on object detection. And for image captioning as well, TST provides detailed captions with accurate object localizations. We also present quantitative comparisons on semantic segmentation. TSTMM outperforms internet-based generalists and task specialists. We observe similar trends for object detection and image captioning. Please refer to the paper for more details. For all the results presented up to this point, test space training trains a model from scratch with random initialization. However, our method can also take off-the-shelf pre-trained generalist models and adapt them to the test space via self-supervised fine-tuning on data from the test space. This can also be seen as aligning a generic pre-trained representation to a given test space via specialization. We find that internet models adapted to the test space match TST performance from scratch on semantic segmentation and outperform on object detection and image captioning. Similar to what we have observed so far, TST models, either adapted or from scratch, outperform internet-based generalists. Next, we present an analysis where we ask, what if we just had a test space and a robot with RGB and depth sensors? This robot does not have access to any external resource like the internet for pre-training data or off-the-shelf networks to create additional modalities. We pose the question, how far can we go with just the test space and physical sensors? We first collect data in the test space with RGB and depth sensors, which can be found on common digital sensory devices like household robots, mobile phones, augmented reality goggles, and so on. Then we programmatically extract canny edges from RGB images and surface normals from depth. Note that these can be done without any external access, since they are simple transformations over RGB and depth sensor readings. In practice, this set of modalities can be expanded to common sensors present on household devices such as audio, motion, and occasionally haptic sensing. Next, we use this collected multimodal data with sensor-based modalities to pre-train a model with multimodal masked modeling. We show a qualitative comparison with a model that is the same as ours, except that it doesn't benefit from test space pre-training. Our model, with only access to the test space and physical sensors and absolutely no other data from the world, is able to learn a good vision representation. Next, we present various analysis experiments for our method TST. For these experiments, we use the procedural generation ability of Proc-Thor to generate similar household spaces. To ground this, two similar or IID spaces imply spaces that are not exactly the same, but share similar visual characteristics like layout and object appearances. We show example of two such spaces here. Note that for the rest of this video, we use IID and similar interchangeably. We begin with a controlled study on measuring the effect of specialization. To reiterate, test space training proposes to build a specialist for a given test space by pre-training on data collected in it. To study the effect of specialization, we begin by asking, is data from the test space particularly useful? What if we replace it with data from a similar space? Does pre-training on an ID space make up for data in the test space itself? To probe this, we pre-train models using test space training for 3 different spaces. As defined previously, these spaces are IID to each other. Next, we evaluate these models on semantic segmentation on all 3 spaces. We find that the performance is best along the diagonal of this matrix. This suggests that the models have indeed specialized to the test space, as they perform better when evaluated on the same test space, as opposed to other spaces. We find that pre-training on the test space is important for specialization and cannot be substituted by a similar space. However, we take this one step further and ask, can we substitute test space data with external data from not one, but many similar spaces? To probe this, we pre-train a model with test space training. The performance of this model evaluated on the test space is shown by the dotted blue line in the curve. Next, we take various number of spaces which are similar to the test space, from 1 to 3,000, and pre-train models on data collected in them. We evaluate them on the same test space. Their performance is shown by the red line. We find that even pre-training in up to 3,000 similar spaces is unable to match the performance of pre-training in the test space, showing the value of specialization. We have seen that the best performance on a given test space is achieved when pre-trained on the same test space. However, we would not expect this model to generalize well to other houses. Let's say we consider data from many spaces. To measure generalization, we take a model pre-trained on these spaces and evaluate on IID held-out spaces, not seen during pre-training, whereas for specialization, we should test it on a single test space. We find that such evaluations reveal a specialization-generalization trade-off. As we add spaces to the pre-training data, the generalization abilities of the model improve as it benefits from diverse data. However, the specialization ability is hurt, as the performance on the test space degrades when external data is added. TST also supports other self-supervised objectives like Dino V2 and MAE. We find that under TST, these objectives also exhibit specialization trends similar to TST-MM, as seen previously. We find that under TST, multimodal masked modeling gives the best performance, and therefore serves as our de facto self-supervised objective. As noted before, TST-MM pre-trains on multiple modalities, which raises the question, is there a single modality that could be responsible for most of the performance boost? Therefore, we perform a modality analysis study where we train different versions of TST-MM with one modality dropped at a time. We compare them with TST-MM and unimodal variant of TST, denoted by RGB only. We find that the performance drop per modality is fairly uniform across all modalities, suggesting that no single modality, but the combination thereof, that is multimodality, is the key driver. We also present an analysis where we study the trade-off between scaling modalities against scaling data size and diversity. When using external data, like the internet, the de facto approach is to scale up data from more diverse sources to improve model performance. However, as discussed before, as we scale the dataset to more and more external non-test spaces, it is unfeasible to have rich set of modalities due to the additional cost and unavailability of such sensory data acquisition over billions of images from disconnected external spaces. Therefore, we scale the data from the 5 test spaces to 3,000 similar spaces, as shown by the x-axis here, which results in a generalist unimodal pre-training. However, on the other end, if we do not scale our dataset size, but instead scale the modalities when we just have the 5 test spaces and can collect unlabeled, multimodal data in them, we go from the unimodal TST-MAE to the multimodal TST-MM. As shown by this plot, we find that, when evaluated in the 5 test spaces, scaling modalities results in significantly more performant models than scaling dataset size by adding data from external spaces. This suggests that scaling dataset size using large-scale external sources can be substituted by scaling with more modalities in the test space. We present more results and analysis in the paper and supplementary material, including more video results on real-world spaces, results on cross-modal retrieval, and analysis of the pre-training data mix for our method. To summarize, we develop multimodal test space training that enables building performant models for a test space. We present 3 key findings. First, we can use rich multimodal data from the test space to substitute large-scale internet-based datasets, which contain much fewer modalities. Next, we can leverage multimodality, that is, predicting the response of one sensor from another, as a self-supervised pre-training objective. And lastly, with the combination of multimodal data from the test space and cross-modal learning, we can build specialist models that outperform SOTA generalist models. Thank you for your attention.